All right, chapter 12. We're going to look at alcohols and phenols in this chapter, mainly just alcohols. We're going to just do a very brief overview of some of the alcohol reactions, how to make alcohols, how to react to alcohols, and do a very short rendition of chapter 12. Phenols, I'll just show you what the structure looks like. We'll talk about a couple ones that are in real life, and then we'll go ahead and move on. Right, so alcohols. Any molecule is an alcohol if it has a hydroxyl group. That OH means alcohol. We notice that in naming, we have a parent chain. So 1, 2 carbons there. That's the eth group or ethane. Notice that that functional group literally changes the name of the parent, ethanol. Same thing here. We have 1, 2, 3, 4, 5 carbons in a cyclic structure. That would have been cyclopentane. Slap an OH group on there and you're cyclopentanol. There's natural hydroxyl groups, cholesterol, vitamin D3. Those are have the hydroxyl groups highlighted there. So we're going to be able to see how we make these. Phenols is a benzene ring directly attached to that with that alcohol. And so phenol is a very interesting compound. We can see that benzene ring integrated into dopamine, the neurotransmitter that is actually the deficient molecule that is prevalent in Parkinson's disease. And we also see that it's in THC and capsaicin down there at the bottom. So we see phenols in naturally occurring things as well. Let's just talk about the acidity of phenols and alcohols for a bit. If we remember that ethanol, that OH group, typically has a pKa of around 16 to 18, depending on how many carbons it has. It's not the best acid out there. We've seen lower pKa's for sure. So the only way to deprotonate an alcohol is with a very strong base. The most typical one is sodium hydride, H minus, can go and do that proton transfer. Reason why H minus is a really awesome base is because hydrogen gas is produced. It has a pKa of 35. So we do see from low pKa to high pKa, this would be a favorable reaction to get the alkoxide ion as the product. Sodium, potassium, and lithium can also be used as well. Those do more radical style reactions. You do not need to know those, but it is a good idea to remember the pKa of alcohols. For phenols, we see a lower pKa simply because the phenol itself has resonance. But again, we're not going to focus on phenols in this chapter. We're going to just focus on our alcohol functional group. All right, we've prepared numerous alcohols via substitution reactions, whether it was SN1 or SN2. We saw that we could have a halide, an alkyl halide, that halogen being the leaving group, can actually undergo a substitution reaction given the correct nucleophile. So for a primary alkyl halide, there's the alpha carbon. Remember, hydroxide with sodium is an ionic bond. We'll see that nucleophilic attack followed by the loss of the leaving group. There's your SN2 reaction. With a tertiary alpha, remember we can't do a backside attack, so we would do an SN1 reaction where the leaving group would leave. We would make our carbocation intermediate, and then water would attack. We would have to follow that up with a proton transfer to get our final product, which is the deprotonated neutral alcohol functional group. Excellent. SN1 and SN2 were our primary ways of making alcohols. We saw a little bit in chapter 8 recently, other ways to make alcohols with our 3 reactions here. We saw acid catalyzed hydration. Remember, acid catalyzed hydration yielded the Markovnikov product, same as our oxymercuration and demercuration, the same isopropyl alcohol there, where the OH ends up on the more substituted carbon. Hydroboration oxidation was our anti-Markovnikov addition product. And those all three were ways to make alcohols. A third method of making alcohols is going to be by using a carbonyl and undergoing a reduction reaction. So just to remind ourselves what the carbonyl functional group is, if we have two R groups on either side of that carbon-oxygen double bond, this was the ketone, the actual carbonyl itself is the C double bonded to the oxygen. That's a carbonyl. So we can have ketones, we can have aldehydes, we can have esters, carboxylic acids. All of those would be carbonyl derivatives, carbonyl compounds, things that contained a carbon-oxygen double bond. Now, undergoing a reduction, let's just remind ourselves of what reduction is. Reduction is gaining electrons to reduce, right? Gains electrons. Oxidation was loss of electrons to oxidize. So this is where we said Leo says Ger, or oil rig was another one. Oxidation is loss of electrons, reduction is the gaining of electrons. Remember, oxidation states are simply a bookkeeping method of electrons. And so we will be able to see how in our general chemistry curriculum, we use charges as our main method of electron bookkeeping. We will do similar in our reactions here, or in our analysis, our bookkeeping method here. But now we have covalently bonded atoms. And so we're going to do slightly different from general chemistry, but the actual definitions of oxidation and reduction still hold true. All right, to determine the oxidation state of an atom, we need to imagine the electrons in the bond, in the covalent bond, as a lone pair, and they go on the more electronegative atom. So we treat all bonds as covalent, and we will break them homolytically. So we're going to be focusing on the oxidation states of carbon. Now we see methanol here. This is CH3OH. And it's spread out in its Lewis structure so that we can homolytically cleave all those bonds. And that's what we did here. We gave carbon the 4 electrons that we would have for its oxidation, or for its formal charge. Same thing with the hydrogens and the oxygen of the OH. Since we're only focusing on the oxidation states of carbon, we aren't going to be separating the oxygen from its hydrogen in the OH group. We're just focusing on oxidation states of carbon. Now, when we look at this carbon, he has 4 electrons. That's how we judged it had a neutral formal charge. Now, if we actually treat all the bonds as ionic and break them heterolytically, what we see is a slightly different story, right? We see that oxygen is more electronegative, so he would get both of those electrons in the carbon-oxygen bond. Carbon is more electronegative than hydrogen, so it would get the others. That is a 6-electron molecule. So it's really the difference between the covalent and the ionic bookkeeping method that will be our oxidation state. So for the oxidation state here of carbon, we take 4 minus the 6, and we have a -2 charge on that carbon. So being able to look at the formal charge and I understand how many electrons the atom owns, subtract it from the oxidation state that we see in terms of looking at the bonds ionically, and we'll get the overall oxidation state of carbon. So here is a generic idea of what we're looking at. In methane, we have a carbon with all hydrogen bonds. That would be an oxidation state of -4. Why? Well, we'll think again, carbon would have brought 4 electrons to the table, that formal charge of 4. And so when calculating the oxidation state, it would be 4 minus. Now, because carbon is more electronegative, it would own all 8 electrons here. 2, 4, 6, 8 because carbon is more electronegative than hydrogen. There's your -4 for methane. Let's do another one just to practice. We did methanol on the previous slide. Let's do formaldehyde. Oxidation state of carbon. It starts with 4 electrons. It has 2, 4. Remember, oxygen is more electronegative than carbon, so carbon doesn't own those electrons ionically. 4 minus 4, 0. Formic acid, the oxidation state of carbon would be 4 minus 2, which is a +2. And in carbon dioxide, the oxidation state of carbon is 4 minus 0. It doesn't own any of those electrons ionically in those bonds because oxygen is more electronegative. So there's your +4 oxidation state. Now, what's important to be able to do is in a reaction, if, for instance, we start with something like formaldehyde and we do a reaction where we become methanol, what type of a reaction was that? Well, I would look at the oxidation state originally of carbon and then the oxidation state of the product. And notice here, if carbon's oxidation state is decreased, becomes more negative, that means it is a reduction reaction, right? Gains electrons. So because we gained electrons here, carbon was reduced. That is another way to make an alcohol, by taking a carbonyl and undergoing a reduction reaction to become an alcohol. So converting that carbonyl to an alcohol requires a reduction agent, a reducing agent. And that reducing agent is the species that will be oxidized, right? We remember redox always happens together. We're going to be focusing on the reduction half of this reaction because it's happening to carbon, our organic molecules. So the reduction of carbonyl overall results in the addition of H2, an H and an H. Notice this pi bond goes away, and we get an H and an H across that pi bond. Adding hydrogen is going to be a simplistic way of looking at reduction. If we were to do the reverse of this, we're taking away hydrogens, we're adding more oxygen bonds. That is going to be oxidation. These reactions, some of them will be able to be reversible, or we'll be able to see the reverse reaction happen with a different reagent. All right, there are 3 reducing agents that can be used. The first one we have seen before. You can use H2 gas with platinum, palladium, or nickel. This method is not really used because of the high temperature and pressure that's required. However, it's still valid in any of our synthesis because, again, you see that 95% yield. That's an awesome yield. Sodium borohydride is a really common reducing agent for aldehydes and ketones. We're going to go through this mechanism. Sodium borohydride is usually in a polar protic solvent. Sodium borohydride is the hydride reagent. It's going to have the H-1 nucleophile that we'll see, and then the polar protic solvent will be able to donate a proton later as an electrophile. So let's go ahead and go through this mechanism first. NaBH4, sodium borohydride, is a boron with 4 bonds, so the boron has a -1 charge. Now it's that hydride that pops off and attacks the electrophile. Remember, we've talked about these electrophiles before. Because of the polar nature of the carbon-oxygen bond, carbon is an electrophile. So the hydride nucleophile attacks the electrophile, kicks up some of those lone pairs so that we don't break up the octet. And then we do a proton transfer with whatever polar protic solvent we have, water, methanol, or ethanol. And there we get our alcohol. Now, these are not the best reactions to do because of the unsymmetrical ketone that could be used, and a new chiral center is created, so you're already getting a racemic mixture with these. Remember, in a trigonal planar molecule, that nucleophile could attack from the left or from the right, top or bottom, and so that's why we get wedge and dashed, right? Racemic mixture all the time. So be very careful with using unsymmetrical ketones where it has two different R groups. Sodium borohydride will make racemic mixtures when you form a chiral center. Now, lithium aluminum hydride is another really reactive reducing agent to reduce carbonyl compounds. Notice here a big difference. Step number 1, step number 2, lithium aluminum hydride, often abbreviated LAH, is very, very reactive. So if you throw water or methanol or ethanol in to the reaction mixture, you will actually just get the deprotonation with water and produce H2 gas, which is probably not what you want to do. Very, very expensive way to do a proton transfer with lithium aluminum hydride. So keep them separate, 2 separate steps there. You will do the nucleophilic attack first with LAH, followed up with the proton transfer of water afterward. Still a great percent yield. Let's go ahead and look at the 2 different structures first, and then we'll get into see the similarities of the mechanism. Again, structurally very, very similar. They are both hydride reagents. And so just like we used the boron to H bond as a hydride nucleophile, aluminum to H bond is very, very similar. Only difference between these two is LAH is much more reactive than sodium borohydride. All right, let's go ahead and look again just to see the similarities. Nucleophilic attack, we're attacking the carbon of the electrophile and kicking up the pi bond so that we don't break the octet, followed by a proton transfer to make, again, the alcohol. Just like sodium borohydride, we would get racemic mixtures if we used asymmetrical or unsymmetrical ketones. Biggest difference here is that we do need a proton source to be added after the carbonyl is reduced. All right, hydride delivery reagents are selective for the carbonyl only with sodium borohydride and lithium aluminum hydride. So looking at this symmetrical ketone, we see that whether we use sodium borohydride or lithium aluminum hydride, we will only get the alcohol as the final product. If you used H2 hydrogenation, you will get reduction of the ketone and you will get reduction of the alkene, right? So be very, very careful using hydrogenation. Catalytic hydrogenation will reduce the carbonyl and the alkene, whereas our hydride delivery agents, NABH4 or LAH, will only reduce carbonyls. All right, now LAH is strong enough to also reduce esters and carboxylic acids. NABH4 is not. NABH4 is only going to be for aldehydes and ketones. It's not going to be strong enough to react with the carboxylic and the ester. And so again, when we do this, what we're going to see is we'll get primary alcohols. Look at both of those alpha carbons right there, and we see that there are 2 hydrogens, an R group, and an alcohol. So that's what we would call a primary alcohol. Now, in this reaction, we just kind of do it twice. Let's follow this along real quick. The big difference is instead of carbon groups, we have this OMe group or OH group if you had the carboxylic acid. So we do our nuke attack. And what happens here at this second step, that first intermediate, can actually roll the electrons back down to form the pi bond and kick out a leaving group. This OMe is going to be what we call a leaving group carbonyl. And so we actually get an aldehyde as an intermediate. But we know LAH will react with aldehydes as well, so you can't stop at the aldehyde. Do another nuke attack, followed by the proton transfer, because now we don't have any leaving groups. No O minuses here. Excellent. Okay, we can prepare diols as well. We talked about them a lot in chapter 9. The preparation of diols is important for us in discussing any sort of alcohol reactions. We want to know how can we make alcohols, so making 2 alcohols on the molecule is going to be important. The first reaction we have here is the anti-addition of our diol. Using a peroxy acid plus H3O and H3O plus will result in the anti-addition that we see of that diol. Osmium tetroxide with NMO is the syn addition of the alcohol, where the OH groups are added on the same side. Just draw 1 for that because it is a meso compound. Now, our diols can also be prepared by reduction of diketones. Having 2 ketones in a molecule can also help make diols. Beautiful.